So, so today we are going to talk a little bit about three things. So the first thing is plotting or visualizing your data, mostly 2D, but also somewhat 3D. Second, we will start. I will give a short introduction to CALFEM for Python, which is a same kind of toolbox that you have from MATLAB, but now ported to Python. I will also have a short introduction to object-oriented programming, because that is something we will go through in some of our worksheets for this week. So these are three parts. So let's start with the plotting part. So plotting in NumPy, plotting in Python, there are multiple options, but for numerical work, the de facto standard is a library called Matplotlib. And the reason it's called Matplotlib is because it kind of emulates most of the plotting functionality from MATLAB. So you have all the commands, you have all the same way of working with it, like in MATLAB. Matplotlib itself also has a very competent plotting toolkit to use. So it's very advanced. But we are going to use the simplified interface in this course. I have provided here, there are some links here to the references to PyPlot, and there are some tutorials here you can use as well. So this is something worthwhile to use. How do you use Matplotlib? So depending on if you're running in a notebook or in Jupyter, the main functionality, main way of importing is it's similar to what you do with NumPy. So import matplotlib.pyplot, which is the simplified interface, and then as PLT. So now we have to prefix all our plotting using the PLT prefix. This is also a kind of de facto standard way of doing it when you're using Matplotlib. The first command here, matplotlib inline, just tells the notebook system that all the plots should be inline in the text. So basically inserted into the text when you're plotting. So let's import that. So the plotting functions in Matplotlib are extremely simple. So it's not required that you have the NumPy arrays for plotting. So you can always plot using lists or other data types that are kind of behaves in the same way as lists. So in this case here, I do plt.plot, and then I have 1, 5, 3, and 4. So basically just four numbers I want to plot. And then I do plot show. And plot show, if you're running a PyPlot in a standalone application, plot show will display a window, or it will display a inline in your editor. So if you run this here, it will plot the values here with a line between them. So that is the default way of plotting. So I can also, let's see here if I can mark this here. So I can copy this to Spider, for example. New file here. Do import matplotlib. If I run this code now, you see there is no plot here, but there is a tab here called plot. And all the plots that you produce are by default in Spider plotted here in this plot tab. There is a way of also you can click here, mute inline plotting. If we run it again here, it will plot inside this interactive window down here, but this is usually not what you want. If you run Python from the command line, so I open an Anaconda prompt here. I'm going to make the text a bit bigger. Just create a simple command here. Example import Matplotlib. Okay. .pyplot. So if you run a Python outside Spider or Notebook, I will show. This is how it will look. Let's see if we can find the play button here. I can save it here as. So when running it standalone, it will bring up a window like this, where you can move around and you can zoom in. So this is one way of doing it as well. So Matplotlib behaves in different ways depending on how you run it. So that was a simple plot. If you want to plot Numpy arrays, which is probably the most used kind of way of using Matplotlib, we have to import Numpy here as well. And then usually when I plot things, I use the linspace command to create a set of x values for plotting. And the nice thing with the linspace is that it's you just give it a range from 0 to 2 pi. And then I give the numbers, how many numbers I want in that range. So I want 50 numbers here. And then I do y equals to np.cnx, and that is an array expression. So y will be an array with the same size as x, but with the computed values with sinus values here. So if I run this, you can see here that x is from 0 to 2 pi, and then you have y is the computed sinus values for these ones here. And then you just plot like you do in MATLAB, plot x comma y, and then plot show like this. And then you get this. And here you can, if you change the value here, for example, to 10 here, you get a much coarser plot here. So linspace, you can determine the resolution of the plot in a nicer way than you use a range, for example. And you also guarantee to have the endpoint part of the curve, the plot. You can change the line type using the third parameter here. So x, y, and a string here. So this says that it should be a red line with circles on it. So now you see filled circles here instead of a line. You can have blue for B, O for circles, and a line. So this is a line with circles and a line between them. So you see a line between those. You can do dashed lines. Then you have double dashes after in the string here. So blue dashed line, like this. You can have crossed lines here using plus signs. Then you have crosses instead of circles. And you can, of course, have a green line that is crossed with also a line between them. So G plus dash. So you see here you have crosses, but you also have a line between them. So for those that are following along, I have a short assignment here just to kind of get you started. So if you have a running notebook, try to plot the function described here. So f of x should be sine x, sine 3x divided by 3, sine 5x divided by 5. And use the linspace function to create the x values. So I give you 2 minutes here to do your own plot here. So, okay, so I will just shortly go through my solution here. So first thing, we need to define x range, np.linspace, and I start from 0, comma, and I will go to 2 pi. And we have 200 points here to make it a nice curve. Y, so np.sin x sin 3 times x divided by 3 plus sin 5 times x. And then we need to plot, so we do plot. And we make a blue curve here, so we do b dash, and we show the plot. So I forgot to put np before of this here as well. It doesn't like that. So this is just a curve. If you continue adding here, you will get a square wave at some point. So that is the way basic functionality of plotting. So you can do a lot of things with Matplotlib. For example, if you want to plot 2 functions in the same plot, you can do that as well. So in this case here, I create a linspace again, and I create 2 y values instead as well. So y1 and y2. And then you can, if you want to plot 2 series, you just plot the first series, x, y1, and then the attributes for that line, x, y2, and the attributes for the other line, other series. And then we plot that. And you see you have 2 curves in the same plot. There is also, you can change the properties of a series using additional parameters here as well. So you have line width equals to 4.0. This is sets the line width of both of the lines that you specify. So all of them will have a thicker line now. It's also possible to, so the plot function will return the graphical elements that you create. So if you want to kind of change the width and size of the different series, you can actually specify here line 1 and line 2. Those are the two series. So if I plot those variables will be assigned, line 1 with the first one, line 2 the second one, and then you can set the line width for the individual series separately. So line 1.set line width will be 4.0, line 2 set line width 8 of the second line, and it looks something like this. So then you have one thicker than the other line. It's also possible to plot. You can set properties using the setP function as well. So if you just return one variable here, this will be a list of all the entities in your diagram. Then you can pass that to the plot.setP command here. That will set the properties of all the entities in this line here, in this line list. So this will make all the lines 8 pixels wide here. It's also possible to plot to multiple figure windows. This is more useful when you have a standalone program that you run. If you're using this in a notebook, it will kind of is useless because you can have just two plots after one another, and then they are still embedded in the same document. So if you run this here, you will have two plots on top of each other here. They will share the same x-axis, but they will be on top of each other. You can do subplots, and this is a bit, the syntax here is a bit odd. You specify in integers the number of rows and columns you want to have in your subplot. So in this case here, I want to create a subplot with 2 rows and 1 column, and this is the first plot. So you create a figure here. This is the first figure you want to plot. This is the subplot 2, 1, 1. And then you plot here, and then you have the subplot here 2, 1, 2. So that is the second plot, and then you plot it. So it's a bit complicated. So this is 2 rows and 1 column, and the first one here is the first diagram, this red one, and the second one here, the blue one, is 2, 1, 2. So the first two here is rows and columns, and the second one is the actual plot you want to plot to. You can do it the other way around. So if you have 1 row and 2 columns instead, then the plots are after each other, and then it will look something like this instead. So then there are 1 row and 2 columns. So that is 1, 2 is 1 row, 2 columns, and then the first plot, 1 row, 2 columns, second plot. I can show you this when you run it, this plot here. I run this from my standalone environment here. It will look something like this. I don't have it. So then instead of having them separately, I get 2 windows that comes up on the screen automatically. So this is where the way it looks when you run it standalone. You can also add decorations to your plots. These are also similar to what you do in MATLAB. So here I do the same thing. I have figure, subplot, and then I put a label X, Y label Y1, and plot, and then I have label X and label Y2 here. You see you have Y1 and Y2, and X here down below. It's also possible to add text to your diagram, and text are added in the diagram coordinate system. So the positions that you put your text is the same positions as in your diagram. So same coordinate system. So I have the text command here. This part here is the position. So that is n pi divided by 2, 0.8 in the y direction. And one extremely cool feature with Matplotlib is that you can take latex command for generating math formulas, and you can add those to the diagram. So using the $ here, you can use the LaTeX math commands here to insert that formula directly into your plot. Let's see here. Why is it not working? So here you see here that this is a function here that this is text here, so it actually sets in the correct math notation. I have a question here about more than 10 subplots. Good question. I have to check that. I haven't done it myself, but I think there are some other ways of doing it as well. But I will check. So you see also that the position here of the formula is actually a bit below here. So it's the center of the formula that is here below here. It's also possible to change the alignment here with the text. So there is a command here or a parameter to your function here, horizontal alignment, and you can center the text. There is also an annotate function here that can create an arrow. So here you set where you want the arrow, and then you specify some other options here. So this is the starting point with the arrow. This is where the text is positioned. So here is this is where the max position goes here, and then the XY text is where the arrow will point. And then you can set where the text should be centered in the horizontal position here. And then you can change the properties of your arrow as well. So in this case, it's black, but you can set blue here as well. That works as well. You can control the axis limits as well using the xlim and ylim commands, and that will constrain the axis to your window, so to speak. So this is the x starting x point, end x point, y start, and the end y end here. So this will be, and you zoom in on this position here from 0 to pi, and then going from 0 to 1 here. So that seems to be correct. You can also change the scale, so having logarithmic scales or in both directions here. This is also one possible, so that is also important. There are some other plotting types as well. You can do histograms, and here you just define how many bins you want to have, and then you put your x values in here and change some parameter. I don't go for, you have to look at them yourself in your in the reference manual here, but there are a lot of diagrams that you can plot in the Matplotlib. Bar charts, you just x and y values here. You plot x and y, so the x values will be the position of the bars, and y will be the value of the bars. The scatter plot, that is a plot points. So you can have Here I scatter X and Y, create random values. I have scales as well, so you can specify the color, you can specify the scale, the label color, if they should be transparent, if there should be some should have edges as well. Legend will add a color scale to your plot, and grid will add a grid, not a grid positions, a grid visible grid in your diagram as well. So in this case, it plots a lot of circle dots here with different scales. And you also have this legend here available. Contour plots. Here we have, this will create 2D ISO lines for X and Y function here. So in this case here, we create a lean space between -6 to 6, and we have 100 values here, and then we have -6 to 6 and 100 values in the Y direction. And then you create something called a mesh grid, which give you X and Y. We can print them out and see what they're. So this will be a list of coordinates per for each point in the grid. So the X coordinates and the Y coordinates for each of the points in the grid. Then you can put an expression here depending on the X and Y variables, and then you can create a contour plot like this. And there are two versions of this. There is contour F, which is a field contour plot, which is this first one here. And then you have a contour, which is a contour plot here with lines for the scale here. And we had a color bar here as well to visualize which colors represent which values in the plot. You can also display images. So in this case here, there is a nice library in Python called URLlib, which can query and download data from the web. So in this case here, I have a URLlib request URL retrieve, and I have an image here that I want to download, and I want to save it locally as a 6502 JPEG. And then I can use the image read command from plot here to read it into an image. And then I can do plot im show to show the image. I remove the axis here because I don't want that, and then show the image here. Okay. Oh, I forgot to run this one. Yes, so it downloaded the image from the web, and then it displayed it here in my notebook. There are some ways if you use images here as well to do smoothing on the images. So you can specify here interpolation method here, and there is a lot of them, and then you can interpolate the images in different ways. Streamline plots, that is plotting the vector field. I don't go through it, I just show it here. So here you see you can do vector fields, streamline plots for those. Bar charts here, the pie charts. Another radial charts like this. You can also plot in 3D. Like this. So it's a quite powerful plotting library. So let's see here. So now we come to the more finite element parts of the course. So so what we have done is in this course is that, or also in some master thesis work, is to create an alternative CALFEM toolkit that is the same contains the same commands that you have in the MATLAB version of CALFEM. It's almost feature complete, but not complete. So it's a subset of CALFEM routines implemented in Python. It uses NumPy for all the array and matrix functions. It has additional mesh generation routines that are not part of the. There are meshing routines in the CALFEM and MATLAB version as well, but the Python version supports both. There is a mesh generator called Triangle, and there is a mesh generator called JMSH, which is a very powerful mesh generator. So CALFEM, the mesh tools will automatically generate the mesh for you and import the outputs from that mesh generator and import it so you get the same aid of topology that you have in CALFEM for Python. And it also has some plot routines that interfaces with Matplotlib. The CALFEM package is divided into several Python modules. There is a module called CALFEM Core, which contains the element routines and some system routines for working with elements. There are some CALFEM utils, the CALFEM utils package, which contains some IO routines and other routines that are not kind of fitting in any package. So it's and then you have CALFEM geometry, which is used to define a geometry which you would use for the meshing later on. And there is a CALFEM mesh package that actually does the mesh generation. And there are some visualization packages as well, so CALFEM.vis and CALFEM.vismpl. So vismpl is uses Matplotlib for plotting, and CALFEM.vis uses another toolbox for plotting. So installing CALFEM can be done from an Anaconda prompt, and then you type pip install calfem-python. So I can do it actually in this notebook, which I need. So this will download the package and install it in my notebook here. So now I have my CALFEM installed. Now I will go through some of these examples that are in the CALFEM manual, but I do it using Python instead of MATLAB. So the general procedure for a finite element calculation is define the model, generate element matrices, assemble the element matrix into the global stiffness matrix, solve the system of equations, and then calculate the element forces. That's the basic. So if we start very simple with a system of springs, we have one spring that is double so it has 2K stiffness, and we have one case with K stiffness, and we have 2K stiffness here, and then we have a force here in the middle here that is applied on this element here. So if you look at the degrees of freedom, so we have 3 degrees of freedom, 1, 2, and 3. We have 3 elements, 1, 2, and 3. So the first thing we have to do is to import all the modules we need. So first thing we need the NumPy module. So we do import NumPy as MP. We do import CALFEM core as CFC. So we use the same kind of naming scheme that we did for NumPy. So we don't have to write calfem.core.something for the commands. We use the Matplotlib visualization toolkit. So we calfem.vismpl as CFB. And then we import math here as well. We don't know why we need that, but okay. Start by creating a topology. And compared to MATLAB, it's a bit more complicated to create the input structures here. So you have to use the np.array to create an array. And then we have the topology going 1 to 2, 2 to 3, and 2 to 3. So we also decided in CALFEM for Python that we use the same index as for the MATLAB version. So indexes here, degrees of freedom always start at 1. So I have to think about that. So degrees of freedom are always starting with 1. Indexing of matrices and arrays are still 0-based, but when we do degrees of freedom in the finite element, we start with 1. we create the stiffness matrix here. So we need a stiffness matrix of 3 by 3. We need a force vector that is 3 by 1. I have to execute this as well. Don't forget. Okay. Sorry for this. Let's see if it works better now. So now I see here, this is a topology. We create our stiffness matrices. Now they're 0, both of them. And then we create our elements. So we start with define k equals to 1500. We set our element properties for the first element to k, element property 2 to 2 times k. And then we do k element stiffness matrix 1 to CFC spring 1e. So this is the same command as in Matplotlib toolbox. And we give it EP1 as an element property, spring 1e. And let's look at those. Seems to be okay. Then we need to assemble these matrices into our global stiffness matrix. And here we can use the asm command, which is also available in the MATLAB version. And we specify here, we want to assemble the first row of the topology matrix here and all the degrees of freedom. And then we specify we want to assemble it into K. And then what do we want to assemble? KE2. So here is a difference from CALFEM for MATLAB is that you don't have to return K and K outside on the left side here, because these are NumPy arrays, those can be modified in place. So ASM will actually assemble K into the K matrix here. So if we run this, you will see that it seems to work here. It assembled this here, and it has been added correctly to the stiffness matrix. Solving the equation here. So now we have to define our boundary conditions. We do that with a boundary condition array here that is 1 by 3. We set F1 to 100 here. And now it's also important to note that when we reference degrees of freedom in arrays that we defined in Python, we need to have, those are 0 based. So this is actually degrees of freedom number 2. So F for the degrees of freedom 2, which is 1 here in the indexing, is 100. And then we do CFC solvec K, comma, the force vector, and then the boundary conditions. So here we have boundary conditions 1 and 3 are set to 0. So the default, so this indicates which degrees of freedom are set to 0. And if we don't specify anything more here, it's assumed that the boundary conditions of those degrees of freedom are 0. Otherwise, you have to specify another variable that contains the specific values for those degrees of freedom that you have prescribed. So let's run this. Hopefully it will run. So the displacement in the second degree of freedom here is 0.013, which should be okay. And we should have reaction forces then both left side and the right side here. So, and that should also seem also to be correct here. Then we can calculate the element forces by calculating the element displacement, and then calculating the spring forces here using a spring1s function. And then we can print them out here. And then we have the forces in the individual springs here. Okay. So let's start, do a bit more complex command here. The bars here. So we have bars that are connected here in 3 bars that are connected together in a single point here and fastened at 3 positions here. Now we have 8 degrees of freedom here. So we start numbering here 1, 2, 3, 4, 5, 6, 7, 8. And those are 1.6 meters wide here. We have a force P here, and it's 1.2 meters here. And the elements are numbered 1, 2, and 3. So we start here defining an EDOF array here. So the first element goes from 1, 2, and then 5, 6 here. Second element goes from 5, 6 to 7, 8. And we have 3, 4, and 5, 6. So 3, 4, and 5, 6. We create our K matrix here, so it should be 8 by 8, and we should have a force vector that is 8. We define some element properties here, so we set elastic modules to 2.0 E11. Define our areas here, and then we combine them together here, E and A1, E and A2, and E and A3. So we don't need to specify stuff like these kind of properties as arrays. We can use lists here. All the functions in CALFEM will handle lists as well as arrays. And then we define our element coordinates here. So this is EX1, EX2. So these are element coordinates for element 1, 2, and 3. Y coordinates for element 1, 2, and 3. This should be similar to what you do in MATLAB. Then we create our element matrices here. So KE1, KE2, and KE3. Use the bar to E command for doing that. It takes element coordinates for X and element coordinates for Y, and then element properties. Works. Then we assemble those using the element topology EDOF here. So we have the first row of that one, and then K and KE1. And then we get a matrix out here. And then we can solve the equations. Now we have to specify the boundary conditions. So we have boundary conditions on 1, 2, 3, 4, and 7, 8. And those are all 0. And then we have at boundary condition number 6. So that is this position 6 here. We have a force here that acts downwards. And that is minus 80 kilonewtons here. And you see here also, this is 0 based for the boundary condition here. So this is actually boundary condition 6, but because of indexing in Python start at 0, so you have to reduce it by 1. And then we solve the equation here by specifying the force vector and the boundary conditions here. Those are all now assumed to be 0. And it seems to be correct. So now we have displacements here at positions 5 and 6. Which are the only ones that are not prescribed in any way. And then we get some reaction forces out here as well. So that seems to be correct. And we can calculate our element forces here using extract element displacements and then the forces in each bar here. So let's take a 10-minute break, and we continue after at 10 past. So let's go sign out. Okay, so now we have a somewhat more complicated problem. We have more bars. So we have a frame-like structure here like this. We have 4 meters here, 2 meters here. We have a angular force acting here on this point. Some areas here are the section areas. And these are the degrees of freedom here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from this, we get a bit more complicated topology. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And now we need to figure out a more systematic way of doing this without explicitly assembling each of the elements into the array, but having some way of doing it more efficiently. So we have 12 by 12 degrees of freedom. So and then we have some extra variables here. We define element properties. All elements are the same, so we have E and A here. And then we specify arrays for our element X values. So EX is array, and then we have list all the coordinates for all our elements, X coordinates. We have Y coordinates for every element like this. We also have, so now we have the possibility to actually do this in a structured fashion without one line for each assembly here. So this is the way we do it in Python here. So we use this zip command here to loop over multiple variables arrays at the same time. So we will loop over the EX array, the EY array, and the EDOF array. And then we have ELX here is the current element X coordinates, the current element Y coordinates, the current topology for the element we are assembling. So now we can create our stiffness element matrix here by using the bar2e command. We just provide ELX, EY, and we don't have to loop over the element properties, but they're all the same. So we just provide EP here. And then we do C, FEC, ASM, L topo, K, KE. We have degrees 0 prescribed displacement here at 1, 2, 3, and 4. At 11, 12, we have our force acting here. So we just do the sine functions here and calculate components here and add them to F11 degrees of freedom 11 and 12. And then we solve the equation system like this. And we can also use one single line to extract all the element forces here. So extract LDs, EDOF, and A will create an ED array with all the element displacement, one per row. And then we can create an array here to store our element forces here. So in this case, we can use the shape 0 here to actually create an array that has the same number of rows as our element topology matrix. And then we can do another loop here to loop at the different to calculate our element forces here. So ELX, ELY, and ELD. We loop over EX, EY, and ED. Then we call bar2S here to calculate element forces once per element. And if we run this here, we get the element forces here in the structure. It's also possible to mix different element types. So in this case here, we have beams here in this frame, and we have bars connecting these beams here together. Now we have some rotational degrees of freedoms here as well. So we have, let's see, we have 1, 2, 3, 4. We should have 18 degrees of freedom in total. And we do like this. So now we have MP0s. So we know we have 18 degrees of freedom. So we calculate the stiffness matrix directly. We specify our element force, and we specify coordinates here. So this uses a different method of calculating. So we, instead of specifying an EDOF matrix directly, we create a coordinate matrix for all the coordinates in our structure, and we specify the degrees of freedom at each node in the structure. So in this case, we have DOF1, which have the 1, 2, 3, 4, 5, 6, 7, 8. So those are the rotational, and that are used for the beam elements. And then we have the degrees of freedoms for the bar elements here, DOF2. And we create our EDOF matrix like this. And then we have create all of our element coordinates here using chord extract here with this part. So this is the for the beam elements, and then we have an EDOF for the bar elements. So we can use the chord extract function here to create our element coordinates instead of using specific element coordinate arrays here. And then we can use this to assemble. First we assemble the beams, and then we assemble the bars. And then we solve the system here like this. And we see here that we have 0, 1, 2, 1, 2, 3, 4, 5, 6 are programmed to 0. So that should correspond to 1, 2, 3, and 4, 5, 6 here. So that should be correct. So this is so using chord extract, you eliminate the use of the EX. You can specify your coordinates using the nodes here. So these are the nodes for the coordinates. And then we have the degrees of freedom in each node for the beams and for the bars. And then we use the chord extract to create our element EX1 and EXY matrices, and also the EX2 and EXY2 arrays. So this was a brief introduction to CALFEM. Next time we will go through the mesh generation part. So in the second assignment here, you will do select one of your the tasks and implement the finite element using CALFEM for Python using manual mesh generation, just like we did in these examples here. So next I will go through a topic that can be a bit complicated. So that's why I want to give you an overview of this notion that is called object-oriented programming. So object-oriented programming is that it's a concept in programming that combines data and methods into a single entity, an object. And objects are often described as nouns such as point, circle, equation, model, square, array, matrix, that you can create in Python. And you interact with these objects by sending them messages. And the messages are verbs. And we have seen this in our string manipulation here. So your string has verbs that, for example, split, that is a verb that you can call on the object to do something. And an object in Python has methods, that is verbs, things that you can do and provide execute actions on the object. And you also have properties that describe attributes and links to other objects. So it can have verbs that you can do action on it, and you can also have attributes or properties that describe the object in certain ways. You describe and define your objects in Python in something called a class. And the class is a blueprint for an object. So it tells Python, my circle object here has the following attributes and the following verbs. So this is a blueprint. When you want to create an object, use this blueprint to create the object. So to illustrate this, I have created an example here that uses procedural or functional-based programming. So in this case here, I have a module or library or function that manipulates points of certain types. So we have a function here that can create a point. So it will return just a simple structure here containing x and y coordinates. That will be a point. We have a function called movePoint that takes an argument here that is the point, and then moves the point certain number of coordinates up x in x and y direction. So you see here it manipulates the point data structure by adding dx and dy. We have a function for zeroing the point, and pass the point, it will zero out this structure here. Set point sets the values x and y, and we can print the point. So in procedural programming, the data structure, that is the point, is separate from the function. So you pass the data structure around your functions, and the functions operate on the data. So to illustrate this, we create the point here, P, with the create point function. We print the point. We can move the point. And you see here that coordinate changed when we moved it. And we can set the point to different coordinates, and we can print the point. But what if we can create a point that knows how to handle itself? So it knows how to move, it knows how to display itself on the screen, it knows how to zero itself, or so create something more intelligent than passing the data structure around. And that we will do with the classes here. So a class definition in Python looks like this. The class point here that defines the name of the class. So this is the name of the template you want to use when you create new objects. When you create a new object, it has to initialize itself to some certain state. So in this case here, when you create an object, it will always call a function called init with 2 underscores here. So 2 underscores init underscore here. Self here is a special variable that points to the actual object itself. So because the class is a template, the functions that are defined in the template will be used on the actual object. So self will actually point to the object you create. So in this case here, I assign self x to 0, self y to 0. So x and y here will be attributes to the object, the new object you create. Every object you create will have its own x and y coordinates attached to it. So how do we create a point object then? So what we do is we create p equals to point, and you can do q equals to point as well. So now we have 1 point p and 1 point q. Oh, I need to define the class here as well. Now I can run this. So now I have 2 objects, P and Q. I can print the attributes of each of the objects here. You can see here both of them are 0, because when you create an object, init will be called, x and y will be 0. So both of them have x and y coordinates that are 0 currently. We can change the attributes of the point by using p.x equal to 1, p.y equals to 2. And you can see here now, if we change one of them, the other one doesn't change. So every object has its own attributes x and y. So those are kind of an entity that is self-contained. One to note here, if you have used other programming languages for object orientation, you have heard that you need to kind of encapsulate the data inside your object from access. And so in this case here, it's you don't want the user to be able to set these variables directly. You want to protect them inside your class and have methods that access these objects instead. That is called encapsulation. So that is, you encapsulate the data inside your object. It could be that x and y actually are database containing a database in the cloud, for example, and the user doesn't have to know about that. But so then you need to protect this implementation. And if the user is able to change x and y, he will also be able to change the workings of the inner object. So what you can do then is you can encapsulate and add, you protect these variables inside here. So instead of using x and y, we prefix them with double underscores here. And the double underscore protects the variable from manipulation outside. So it's hidden from the user. So in this case, if we define our class like this, and we assign, now we add 2 parameters here that to give the point when you create the object. So in this case, you create the point, x and y is 2, that will call and set these 2 variables here. So this will work. But if we do this now, we will have a problem. So as we hit our x and y storage here in our object, we can't access the attributes here anymore. We can't even do this, because this is a special meaning in Python, the double underscore, that which actually hides the object, so it can't be accessed from the outside object. So how do we solve this? So we need to be able to get access to inner objects. So what we do then is we add some methods to set and get the values of the internal variables here. So we have a set x, set y. We have a set x and y, just a convenience function. So now we can set the values of our objects here separately. So we can do p.set, we can do p.setx, and so on. And we can add additional function for actually accessing our x and y coordinates here. So in this case here, we have x, and it returns self.x here. And now we can use the object like this. We create our object 12 by 13, and we can set the positions in different ways, and we can use x parentheses here to access the values here from the object. However, it would be nice to be able to use these properties like with the first example we had, that the user can just assign p.x. And actually, we have that we can do this in Python using something called Python properties. And properties is a way of providing the object a way of assigning attributes that are really easy to use, but you still maintain the control of the inner implementation of your object. So in this case here, we have the same as we had before, x and y we can assign here. We have our set x, set y, we have our get x and get y instead of x and y. But then at the end here, we define this. So here we have x equals to property. And property here means that we need to specify one function for retrieving the value. So in this case, get x, and one function for setting the value. This means now that we can actually skip using set. We can actually use the original property already attributes that we can assign them directly like this. So we can use px equals to y and the value, and py equals to another value. But internally, you can see here that when we assign x here, it actually calls set x automatically for us. And we also set y here is called when we set the y value here. And when we print x, it will call get x. And if we print y, it will get y. So this is a way of providing a very easy to use interface to your object. And actually, what I do when I implement clauses myself is that I skip the get and set methods until I need them. I define them as normal attributes. And if I want to make sure that something is correct or need this protection, I can add it afterwards. And the programs using my objects can still continue using them like before. They don't even know that it's a property anymore. You can have other methods as well. So instance methods is these verbs we need. So for example, if I want to move my point, I need a move method. So here I have added a move method here with provides dx and dy here to move the object. All of those are, every method or access method of an object needs to have the self parameters first. You don't call the self. The self is provided by Python automatically. So when you're using the object. So in this case here, when I call p equals to p0 equals to point, it will call init here with a new memory location for the new object. So that will be contained in self. And that is handled by Python automatically. P1 here, also point. P-move here, same thing with the self method that is automatically passed on to Python here. So the move method will be called with the self being P0. And now you see it moved the object here. Another method that could be useful when you do object is the ability to copy the values from one object to another object. So in this case here, I have added a copy from self and then a p here. So it will copy the values from the object p and assign the internal variables for the new object to these x and y coordinates from the parameter here. And then I can do p1 copy from p0. When I print this, it should print the same coordinates as p0. Let's see. Yes, so after I copied it, it has the same coordinates as P0. There are some other instance methods here that could be important. We had showed init before, that is called when you create a new object. It's used for initializing the object, setting the state variables correctly, and but there are some other ones as well. There is an object called str, which is when you print an object. This method is called. It tells the object, I need a string representation of my object. Could you provide that for me? And if you do print without this method here, you can see here that if you print p here, so this is a point. It doesn't. So Python doesn't know anything about the point. So the only thing it can do is print out something cryptic like this. Okay, this is a point object at this memory location. Not so very useful. So what we can do, we can provide an str method here. So in this here, I have provided an str method. It contains, just prints out point here, and that prints out the internal state of the point. And returns a string that is a representation. So if we do run it here again, instead of printing this strange cryptic thing, we get out print point here, and we have the coordinates 42 and 84. So that seems to be, and that is much nicer than having it print out just the memory location of the object. When you have defined a class, it can be used just like any data type in Python. So there is no difference in your own classes and Python's own data types. So for example, here I have a loop here that creates random points. So it just puts in random x and y coordinates and adds them to a list. So the list can handle your points as well as floating points or other strings. There's also a way of doing it in a shorter way like this, but you can do it. You can try it out yourself if you want. So what you can do now, if you have the string, you can very easily print out your object. So in this case here, for p in points, print p. So print will automatically call the correct str method of your implemented point object. So now it will print out here using the str method we defined all your points. And variable reference work the same way with Python as I showed you before with the Python data type. So you have P0, P1. Those are 2 point objects allocated in the memory of your computer. Then we say P2 is equal to P0 and P3 is equal to P1. And we check how the IDs here work here. So now we see here that the first 2 ones are different. And you see here, if I assign P2 to P0, it gets the same memory location. And same thing with P3 here. So everything works the same as the built-in data type. So basically, classes enables you to create your own data types that you can use in your code. And in our course here, we'll be implemented a number of different classes here. So we will have one class that is the model that describes your finite element problem. We will have a result class that prints out your objects, your results. And we will have a user interface classes that defines your window. So this is why I'm going through this now, because we will mention this in the worksheets as well. You don't have to think too much about it. It will in the worksheet you will be step by step implementing your classes. But I want to give you this overview of what object orientation is as well. Another thing that is very important in object-oriented programming is that you can inherit functionality from existing objects. So suppose now that we have implemented the point class, it's done, and we have a lot of functionality there already. We know how to set the position, we know how to move, we know how to print ourselves. So now we want to create a circle. So a circle also has a position, but in addition to the position, we also have a radius. So now we can create a circle without re-implementing everything we have from our point. We can actually reuse a lot of it. And what you can do then is you define a class here like this, class circle point. This tells that Python that circle will inherit the same functions or methods as in point. We need to create a new init method here that adds a radius parameter here. And the first thing we do in this init method is we need to call the points init method to make sure that the data structures from points will be initialized. So we just do super here, and the super function returns you the class of the parent class, in this case point. And we call the init method of that class here with x and y coordinates. And then we assign our own R attribute here. We provide set R and get R method here. We have our own copy from here, which adds, it copies also the radius here. And we update the string here to also provide a radius output. And we add an R property here so that we can access it like a property. So the nice thing here, now we can actually create two object types. We can create the point and we can create a circle. We can set on the circle, we have an additional attribute here called a property called R, which we also can use. We can call p.move, but we also have the possibility to call c.move, because now circle inherited all the methods of the point class and all the functionality of the point class. And then we can print both of them here now, and it should print the point here, and we print the circle like this. That was inheritance. Another way of combining classing is using something called composite clauses. So instead of inheriting functionality, you can create new classes that combine several different objects into a single class. So, for example, we have a geometric line, for example. It has 2 points. So internally here in this class here, we create two variables, p0 and p1, that creates, so by default, it creates 2 point objects. We have a possibility to set p0, p1, set p1, and get, we can get and set the points. We have a string method that calls the string method here from points here. And then we have properties p0 and p1. And now we only provide a get method here. So by only providing a get method, you get something called a read-only attribute. So in this case, the user can only extract the value from that, but they can't set the property. I'll show you how we can do that later. So you define that. And if we run this here now, we can create a line like this, and we can assign p0.x equal to 0, p0y equal to, so the line has actually 2 objects of type point that it owns. It doesn't inherit it. It actually is a composite. It contains 2 points that you can use. But if we do it like this, let's see what happens here. So you have an error here. So you can't set the attribute here. So p0, this is not possible because p0 here doesn't have a set method here. This is okay because it accesses the properties of the p0 point, and you can assign that property 0. But you can't assign the point here. And this could be something that you do by design. You don't want the user to be able to replace the point objects. But you can actually easily change this here. So instead of having, you add get p0 and set p0 here, redefine the class, and run it again. And this will work. So now you can have you can assign p0 and not a new point object. Now you can see here that when we print them out, you can see that it prints out p0, the position here, and you can have also this point here. So we use the str from the point object to print it out as well. Now this is the same example we had before. You can, of course, on the line class, you can the national thing is to have a method that can calculate its own length. So in this case, I can have get length here, and then I can have a property called length that calls get length automatically when you assign. So if the user accesses the line.length, it will automatically calculate the length and return that back. And this can be used like this. I really didn't define that. This, I'm going to run this example here. You see it automatically. So at this first instance, I'll access this property length. It will call get length and calculate the length and return it back here. The final feature object orientation that can be useful to know is polymorphism. And that means that the correct method that is called is actually determined when depending on which class instant you have are calling on. So if the method is not available in the current instance of the class, it will look in the parent class for that method and continue searching. And what polymorphism enables is you can handle mix of instances of different types, and you can ensure that the correct method is called depending on the actual data type. So what that does actually mean. So for example, if we want to have a drawing program that creates a lot of shapes, and we want to add different shapes to a global list that actually does the drawing. So in this case here, I have a point, I have a circle, I have a line, and I do something really strange like this. I add a number here, and we will see what happens here. And it works. And so it calls print on every shape in the list. But it looks kind of strange here. So 42 is a floating point number. Is that an object? In Python, the floating point number is actually an object. And this final here, print, is actually the same equivalent of doing print 42.0.str. So the floating point value is actually an object that you can call methods on. And it has a string method here, and it's called like this. So by this here, you can in a list, you can mix and match different data types. And as long as they have a str method, it will find the correct str method here to call. So in this case, it's a point. So it will find the point str method, and it will find a circle str method. It will find a line method, and it will find a floating point str method. So that was what I had today for the lecture. I will show you also the current task here. Assignments. So we will be working with assignment 2. Assignment 2 here, like this. So we will define a finite element program, and we will start with the model defining several classes that will make up the finite element program. So we will have one class that is input data that will define all your input data to your problem, and you will see here you define here, for example, thickness, element properties, your coordinates, your element topology here, and you define that in a class. And then we also will define a class for output data, and that object will handle the results from the calculations. So we'll start by defining empty variables here that will be used later on. We will define a solver class that will solve your problem, and it will actually, in the execute here, it will actually do the input data, take the input data, and then use that to solve the problem. And then we will have a report class that will actually be used to do the report of the output data. So this is what you're going to do in the next step, and you will have you can implement a plane stress problem. You can do a 2-dimensional heat flow problem or a ground water flow problem. So you choose one of them, and you use one. You will use that problem for all the for an entire project, for all the worksheets. So you don't have to implement a program that solves any of these problems, only one of these problem types. And here also at the end, these are the input data you will use to test out your problem. There are different, one for each of the problem types. So this is what you will do in the next worksheet this week. It seems to be a lot, but it goes through step by step what you need to do. So that's why I wanted to show you the object orientation already now, because we will use some of this object orientation in this worksheet to handle data. So the idea with the objects for input data is that you can create, for example, an input data object. You can have multiple input data objects which you can pass to your solver. So you can solve multiple problems just by passing a different input data object. And then you can get your results in an output data object for the different problems you solve. So using objects here will make your finite element solver a bit more flexible. So I will stop the recording now, and you can